Hello student, welcome in ROSE project in 12th standard, which is conducted by Lect Shikshan Samsthas. Myself, Minal Hemant Pawar from Sadhguru Gadge Maharaj College, Karad. My subject is physics. Today we are going to learn topic number 10, magnetic effect of electric current. Already we have seen total 4th lecture of magnetic effect of electric current. Today we are going to take lecture number 5 of magnetic effect of electric current. In this lecture we will see magnetic lines for current loop. Second one, circular loop carrying current as magnetic dipole, Ampere's law, application of Ampere's law. Now first of all we will see magnetic lines for current loop. Now what is mean by the magnetic lines? If there are magnetic field, there is magnetic lines of forces. Now see here that in this diagram we know that magnetic field at a point P on the axis is given by. Last lecture we have seen magnetic field at a point P on the axis is Pz is equal to mu 0 I r square upon 2 z square plus r square 3 by 2. This is the magnetic lines for the current loop. This one is the current loops, the magnetic lines. If their magnetic field is there, is magnetic lines are there. This diagram shows that the magnetic lines for current loops. And this equation is the indicate the magnetic field at a point on the axis. Now see here, as a special case, the magnetic field at the center of loop is obtained from equation when z is equal to 0. If the center of loop, we can substitute the value of z is equal to 0 because the only along the z axis the magnetic field is present. So we get the Bz is equal to mu 0 I r square upon 2 in bracket z square plus r square 3 by 2. If there is center of the loop is obtained from the above equation by letting the z is equal to 0 here. So if z is equal to 0, therefore b0 is equal to z is equal to 0. So b0 is equal to mu 0 I upon 2r. By substituting this value, we get the like this equation. b0 is equal to mu 0 I upon 2r at the center of the loop obtained by z is equal to 0. Substituting the value of z is equal to 0. Now see here the magnetic field lines from the circular loop, from where in this figure as shown in figure, the direction of the field is the right hand thumb rules. That we already have known what is the right hand thumb rules or what is the right hand thumb loop statement. Now here we have to use the curl plumb rules. The curl plumb rules of your right hands along the circular wire with the finger in the direction of the current and the stretched right hand thumbs give the direction of the magnetic field. Thus is the upper part of the loop is seen by the regarded north pole and the lower part of the loop is the south pole of the bar magnet. Now see here the magnetic field lines from the circular loop. Already we have known the right hand thumb rules. Now here we are going to use the curl plumb rules. Now what is the statement of curl plumb rules? See here, by using this diagram we can understand how the curl plumb rule is applying here the magnetic lines for the current loops. Now see here is the plumbs, here is the stretched right hand thumbs. These stretched thumbs give the direction of the magnetic field, and this outstretched there is curl fingers, that is curl finger indicated there. By using the upper part of the loop, there is upper part of the loop seen regarded at the north pole and the lower part of the loop is the south pole of the bar magnet. If there is magnetic lines, here is the magnetic lines, here is the magnetic field. So we have to consider here is the bar magnet is here. Here we have to use the curl plumb rules. That curl plumb rules indicate the stretched thumbs indicate the direction of magnetic field and the upper part of the loop is regarded the north pole and the lower part of the loop is regarded the south pole. Now we have to know the statement of right hand rules. The right hand rule, the sum indicate the direction of the current and this curl finger indicate the direction of magnetic field is there. Now here curl plumb rules, the stretched thumb indicate the direction of the magnetic field and the upper part of the loop is seen in the regarded north pole and the lower part of the loop seen as the south pole of the bar magnet. Now see here, the circular loop carrying the current as the magnetic dipole. Now circular loop carrying current in the magnetic dipole, the behavior of the magnetic field due to the circular current loop at the larger distance is very similar to the electric field of the electric dipole. If there is magnetic field, there is magnetic dipole is there. Electric field is there, electric dipole is there. From the above equation for Bz, that Bz equation we have seen in the last lecture, at the larger distance from the loop along it, Z is greater and greater than R. So we get Bz is equal to mu 0 IR cube upon 2Z cube. There is area of the loop is A is equal to pi R square. If the substituting the value of pi R square, here is pi R square. So we get there Bz is equal to mu 0 I A upon 2 pi Z cube here. That is A is equal to pi R square. The magnetic moment of the circular loop is defined as m is equal to I into A, where A is the vector of the magnitude A and the direction perpendicular to the A. So Bz is equal to mu 0 IR cube upon 2Z cube. Then Bz is equal to mu 0 IA 2 pi Z cube. That is substituting the value of A is equal to pi R square is here. Now see, that is substituting the Bz is equal to mu 0 IA upon 2 pi Z cube here. Now see, Bz is equal to mu 0 m upon 2 pi Z cube. We get the value of Bz is equal to mu 0. Substituting the value of Ia is m. M is the magnetic moment. Magnetic moment means I into A. So we get mu 0 m into 2 pi Z. Instead of this Ia, we can substitute m here. That if there is that is adjustmenting here, we have to do here adjustment. If they are adjusting the term 2 here and if 2 here, so in their numerator or denominator both side multiplying 2, so we get Bz is equal to mu 0 2m upon 4 pi Z cube. That along the Z axis, the magnetic dipole along the Z axis. So similarly, the electric dipole's equation also we can write. Electric field is there is electric dipole. E is equal to 2p 4 pi epsilon 0 Z cube. That is the electric field circular carrying the current as the electric dipole. P means the electric dipole moment. M is the magnetic dipole moment. So this three equation is gives that three equation is indicate the that first equation indicate the magnetic dipole here, and last one equation is equal to 2p 4 pi epsilon 0 Z cube is there. Now see here, next article is what is the Ampere's law. Now that Ampere's law, we know that distribution of charges is given. One can obtain the electric field by using inverse square law. By using the Biot-Savart's law, in this Biot-Savart's law, we have to use the inverse square law. The distribution of charges is or spherical or cylindrical symmetrical with the help of the Gauss laws also. In last section, we have already learned the electrostatics topic. In this electrostatics, we already have seen the Gauss law. Now we can find the net electric field. Now see here, on the similar there magnetic field produced by the distribution of current. Ampere law used for distribution of currents here. The distribution of currents, the Ampere laws find out the magnetic field. See here, by using we have studied Biot-Savart's law. Ampere's law can be derived from the Biot-Savart's law. The Ampere's law can be derived from the Biot-Savart's law. This law is due to the Andre Marie Ampere's in 1775 tends to 1836 after that SI unit of current is named. That is Ampere's law is here. That is line integration of BDS is equal to mu 0 I. What is the statement of this Ampere's law? The line integrals of magnetic field of induction along any closed path is equal to mu 0 time total current flowing through this closed path. That is the Ampere's law. That is the statement of Ampere's law. In mathematical forms, we can write the line integration of B ds is equal to mu 0 I here. Now see, this sign is indicate. This sign indicate the integral to be closed loop is called Amperian loops. That is known as Amperian loops. That Amperian loops means the circle drawn around the any loop. Now see here, what is meant by Ampere loop? Now see here diagram. In this diagram, see here, in this diagram there is total 4 current is there, I1, I2, I3, I4. Now see as cross section of 4 long straight wire. Here we have to taking the 4 long straight wire. The 4 long straight wire carrying the current I1, I2, I3, I4. That is into or out of the planes. That is the into or out of the planes. That is an Amperian loops. The imaginary circle drawn around this long straight wire is known as Amperian loop. Amperian loop is drawn to the in circle of 3 current wire. Only 3 current wire is encircled here. See, I1, I2, I3, and 4th one is not inside this encircled. This is only how many currents are encircled there. Inside the encircle there I1, I2, I3, that is encircled there, and I4 is not inside there. Only 3 current is inside here. See, I4 is not the 4th one. As the current goes perpendicular to the plane of the paper, that is current is perpendicular to the plane of the paper, here B is. Now see here, only 3 current is inside the encircled Amperian loops and I4 is the outside here. Here also using the curl-plumb rules. In these curl-plumb rules indicate, stretched thumbs indicate the direction of that field and outstretched thumbs indicate the direction of, that is outstretched thumbs indicate the direction of field and the curl finger indicate the direction of magnetic field. Sorry, these outstretched thumbs indicate the direction of magnetic field and this curl finger indicate the direction of currents. See, that is the statement of curl-plumb rules used here. Now see, here how many current are inside there? I1, I2, I3 current inside the Amperian loop. That Amperian loop is drawn to the in circle of the current and 4th one is the outside, that is the Amperian loop. Here, in the plane of the paper, the length of element Amperian loop. By using the Ampere's law, B dot dl is equal to B dl cos theta. Integration of B cos theta dl is equal to mu 0 I here. Mu 0 I here. Thus, the integration over the product of length dl of the Amperian loop and the component of magnetic field B cos theta tangent to the loop. We use the curl-plumb right hand rule, so we can mark the current with positive sign or negative sign. Now see, the curl the right plumb along the Amperian loop with the finger in the direction of integration, then current in the direction of stretched thumb is assigned a positive sign and current in the direction opposite to the stretched thumb assigned a negative sign. So, for the distribution of current as shown in here, I1 and I2 coming out of the paper parallel to the stretched thumbs, these are positive. I3 on the other hand is going into the plane of the paper X. Now by using the curl the right hand plumb along the Amperian loops with the finger in the direction of integration, that current in the direction of stretched thumb is assigned a positive sign and current in the direction opposite to the stretched thumb assigned the negative sign. For the distribution of current, I1 and I2 are coming out of the paper and parallel to the stretched thumbs. That is I3, which is the negative signs is there, and I1 and I2 is the positive signs there. So that equation we can write the line integration of B cos theta dl is equal to mu 0 I1 plus I2 minus I3, that is the equation 3. That is, the current I4 is not within the Amperian loop. As the integration over a full loop, the contribution of I4 the cancel out. So equation 1 represents the Ampere's law or Ampere's circuitable laws. Here see, by using the Curl-Plumb rules. In this Curl-Plumb rules, that is with the finger in the given the direction of the integration, and this current in the direction of stretched thumbs is positive sign, current in the direction opposite to the stretched thumb assigned to the negative sign. So only 3 current inside is this Amperian loops, and the I4 is not inside the Amperian loop, so I4 is cancel out. Now see, consider long straight wire carrying the current I. This is the application of Ampere's law. That is, B and DL are tangential to the Amperian loop, which is circle here. Now see here, when we see circle here, so this is the application of Ampere's law. That is, magnetic field due to the long stretch wire carrying the current I, and B and DL are the tangential to the Amperian loop, which is circle here. B dot DL is equal to B DL. So we can write, instead of DL, we can write R D theta. By here, the field B at a distance R from the wire is given by. So we get, that is the last equation, B is equal to mu 0 I 2 pi R. So substituting the value of the magnetic field along the long straight wire, that we already have seen that last lectures, that is B is equal to mu 0 I upon 2 pi R. The substituting the, by we have to taking the line integration of here by applying the Ampere's law. The line integration of B dl is equal to 0 to pi 2 pi mu 0 I upon 2 pi R. Substituting the value of B here, so we get mu 0 I 2 pi R R d theta. R cancel here. Here the value of d theta is 2 pi. So we get the value mu 0 I. That equation we get. This is the agreement with the Ampere's law. This, the magnetic field of infinitely long wire is proportional to the current but inversely proportional to the distance from the wire. Here, by using this diagram, we can say that is the long straight wire carrying current. Here is I be the current flowing through this long straight wire. Here is encircled wire here, encircled drawn around this current carrying wire. It is known as Amperian loops here. The magnetic field is along, R be the radius. So instead of dl, we can write R d theta. That last equation, by using the last equation we obtain here. Here, by using the last equation, B dot dl is equal to B dl B dot R d theta. The field B at a distance R from the wire is given by B is equal to mu 0 I 2 pi R. That 0 tends to 2 pi mu 0 I 2 pi R R d theta mu 0 I. This is the agreement with the Ampere's law. That equation shows that magnetic field of infinitely long wire B0 is equal to B is equal to mu 0 I. Here, now say the next applications of, that is Ampere's law, magnetic field of solenoid and toroid. Now we have, first of all we will see magnetic field of solenoid. That is, we already have learned in 11th standards. Solenoid means what? The consider long closely wound helical coils of the conducting wire. We assume that the diameter of the coil is much smaller than its length. The figure shows that the diagram of cross section of current carrying solenoid. What is meant by solenoid? The solenoid is the long closely wound helical coils of the conducting wire. The diagram shows that here. So the density of magnetic lines along the axis of solenoid with the solenoid, the certain distance away from the wire is uniform and the magnetic field is parallel to the axis of solenoid. In the last year we have seen what is meant by solenoid. Now see here how to solenoid here is applying here. Here That first of all, see diagram. By using this diagram, we can say this diagram is here. The solenoid is the closely wound, this shaped, the schematic diagram of cross section of current carrying solenoid is here. Now see what is meant by solenoid here. Solenoid is long straight, there is wire here, closely wound helical coils of conducting wire here. Now see, these lines are widely spaced outside the solenoid, hence the magnetic field is weak. If the magnetic lines are widely spaced outside the solenoid and magnetic field is weak, for real solenoid of finite length, magnetic field is uniform as the good strength at the center and comparatively weak at the outside the coil. There are good strength at the center of there and comparatively weak at the outside the coil. The magnetic lines are widely spaced outside the solenoid and magnetic field is weak there. For solenoid finite length, magnetic field is uniform as the good strength at the center and comparatively weak at the outside the coil. Weak at the outside the coil. For the application of Ampere's law, we can write the line integration of BDL is equal to mu 0 I. That is the Ampere's law. Now see Ampere's law. Now first of all we will see the diagram here. By using this diagram here, see, here is the rectangular shaped ABCD here. Ampere's law is the part of long strand and the dot shows that current is coming out and the cross show that current is going in the plane of the paper. These are Amperian loops A, B, C, D. Inside there, here is magnetic field is present. Outside there, magnetic field is very weak. So, by taking the reference of this diagram, we can write here, this equation, we can write over the rectangular loop A, B, C, D. By taking the reference of this diagram, that A to B, integration of A to B, BDL plus B to C, BDL plus C to D, BDL plus D to A, BDL is equal to mu 0 I. By taking the rectangular loop, loop is here, so we can apply here loops by using the Ampere's law. A to B, BDL plus B to C, BDL plus C to D, BDL plus D to A, BDL is equal to mu 0 I here. So, by using this diagram, that we are applying here A to B, B to C, C to D and D to A here. In the above equation, I is the net current circled by there. Only remaining terms is here B dot L, other terms is 0 because inside their magnetic field is present only. Outside and these both pins are parallel, there are zeros value. Here only inside is present here. Which one term is only remaining here? Only here. Only this one term is remaining, other term will become 0. So we get this equation. We get equation that B dot L, this only term is remaining, plus 0 with mu 0 I. The second and fourth integral are 0 because B and D are perpendicular to each other. And third integral is 0 because outside the solenoid B is equal to 0. That's so the second and fourth integral is 0 because B and DL is perpendicular to each other. And the third integral is 0 because this is outside the solenoid. So the net current, the number of the turn per unit length of the solenoid and the current flowing through the wire is I. Then net current coming out the wire is here. That last equation we get I is equal to NLI, number of the turns. So from equation BL is equal to mu 0, value of I, substituting the value of I, mu 0 NLI. LL cancel. So we get last equation B is equal to mu 0 NI. Although the above result for B is obtaining for ideal solenoid, it is valid for realistic solenoid, particularly when applied to point in the middle of it, but certainly near the end, solenoid can be designed specific value of B, choice of I and N. This equation indicates magnetic field due to the long closely wound solenoid. P is equal to mu 0 Ni. This is indicate the magnetic field due to the solenoid. This is the application of Ampere's law. Now see, today's lecture we have seen magnetic lines for current loop, the magnetic lines for current loops of magnetic dipoles and electric dipole, what is the Ampere's law, applications of Ampere's law to find the magnetic field due to the long straight wire and magnetic field due to the solenoid. Thank you very much.